Hello friends, I am Subhash Kadlak, Assistant Professor, Chemical Engineering Department, Bernoulli Academy of Management and Technology, Ratnagiri. Today we will discuss Bernoulli Equation. How will I have the Bernoulli Equation and its application? For that, first we have to understand the different fluid flow. Or we can say different flows, as we have static flow, kinematic flow and dynamic flow. Static flow means study of fluid when it is in a rest position. Second, kinematic fluid, in which we will study the fluid when it is in a motion, but in which we will not consider the forces causing this fluid motion. And the third is a dynamic fluid. In dynamic fluid, we have the study of fluid when it is in motion, in which we will consider the forces causing the flow. In which first we will see the equation of motion. The equation of motion, in which according to the Newton's second law of motion, the net forces acting on a fluid element, will consider a fluid element in the mass of the fluid. On this fluid element, the net forces acting in the particular direction, says x, is a product of mass of the fluid element and the acceleration in the x direction. Here we have the equation, x is equal to mass into acceleration in the x direction. Then, when fluid is in motion, on that fluid several forces are acting. These are the some forces: gravity force, pressure force, viscosity force, forces due to turbulence and force due to compressibility. Then we have the net forces, that is, we have in above equation Fx is equal to m into Ax, in which the left hand side, that is the Fx, is a net forces. That net forces is a combination, or we can say the summation of all these forces. Fx is equal to Fgx plus Fpx plus Fpx plus Ftx plus Fcx. Here the x is the direction of flow, in which the last term, that is the force due to compressibility, if we neglected this, or we can say in the study when the situation is likely in which the forces due to compressibility are not observed, in this time those forces or those study will done is observed in the Bernoulli equation of motion. That means we have the Bernoulli equation of motion, in which we have only the first four terms, first four forces terms. Secondly, when we consider the likely compressibility, likely we consider the turbulent force is also absent, or we can say the negligible, then we have the remaining only three terms, that is the force due to gravity, pressure force and the viscosity force. Those equation we have is the Navier-Stokes equation. And the third one, in which we will consider only the forces due to the gravity and forces due to the pressure. That means the forces due to the viscosity is negligible, forces due to turbulence is negligible, forces due to the compressibility is also negligible. Then we have an equation Fx is equal to Fg in x direction plus Fp in x direction, that is the Euler's equation of motion. Then by using this basic Euler's equation of motion, we have modified Euler's equation of motion, obviously by deriving it. For that we have to consider a fluid element. On this fluid element we have the forces acting on it, in which we just consider the, as we seen, the forces due to gravity and forces due to the pressure. By taking the resultant, we have these net forces, and we have, this is the we can say modified form of a Euler's equation is integration of, instead of saying integration, we can simply say it's a dp by rho plus g dz plus v dv is equal to constant. That is the modified Euler's equation of motion. By using the modified Euler's equation of motion, we'll have the Bernoulli equation. For a derivation of Bernoulli equation, we have to make some assumptions. Likely, fluid is ideal, flow is steady, flow is incompressible, and flow is irrotational. Here we have the Bernoulli equation simply by taking integration of the modified Euler's equation. Likely, here we'll take an integration of the Euler's equation, and after simplifying, we'll have the P upon rho g plus V square upon 2g plus z is equal to constant. Earlier, that in Euler's equation, the first three terms is equal to 0. By taking integration, we have this is a constant. Then we have the first term, the P upon rho g, we can say it's a pressure energy per unit weight of fluid, or also called as pressure head. The second term, that is V square upon 2g, is a kinetic energy per unit weight of fluid, also called as the kinetic head. And the third is the Z, it is the potential energy per unit weight of the fluid, or also called as the potential head, is equal to constant. That means the Bernoulli equation is a summation of all energy, and that all energy should be a constant. That is regarding the Bernoulli equation. How will I have the Bernoulli equation? Here are some applications of the Bernoulli equation. Bernoulli equation have the wide application, but by considering the incompressible fluid. Incompressible means obviously we say it's a liquid, in which when we consider the energy involvement, then we have the different application. But when we consider the measurement of the fluid or measurement of the fluid flow, for that we have the three different applications: venturimeter, orifice meter, and pitot tube. In venturimeter, we will calculating the actual flow rate by deriving. We have the actual flow rate, in which the terms involved likewise the coefficient of venturimeter, then the area at the pipe, area at the throat, and the height that h is the differential U-tube manometer height. Likely we have the orifice meter also. In orifice meter also we calculating the actual flow rate. And the last one is the pitot tube. In pitot tube we will calculating the local velocity. These are the applications of Bernoulli equation. And for that, here I have the array class. Thank you for your valuable time.